Okay, all right. There's your energy released in alpha decay. It's the same way we're going to figure it out for beta decay. Okay, next slide, beta decay. Right, again, remember beta particle is an electron, right? And it turns out that there's also a neutrino, and I'm not entirely sure what a neutrino is, to be honest, that gets released along with that electron. But a couple of, right, the neutron changes into a proton, an electron, and a neutrino. Like I said, I'll admit that I'm not entirely sure what a neutrino is, but it's effectively nothing. That's what confuses me about it, because no charge and effectively no mass, because it's so small, right? Here's our example of beta decay, right? Again, the carbon 14, carbon 14 decays into nitrogen 14 plus the electron plus the neutrino. So again, conservation of nucleons, 14 to 14. Conservation of charge, 6 protons becomes 7 protons minus 1 for an electron. So 6 and 6, plus that neutrino, which again, like I said, I'm not sure what a neutrino is, to be honest. Right? Yeah, I don't know what effect the neutrino has. I'm not even sure how they found this thing, because it's chargeless and massless. So I'm not entirely sure how physicists found the neutrino to begin with. All right, so that's beta decay. We can potentially have a beta positive decay, which is the same thing, except a positron is emitted. So notice, if it's beta positive decay, then 10, you lose a proton, but a positive charged positron gets produced. So we still have conservation of charge, right? Okay. Continuing on. Right, the energy released is the exact same process, right? We're going to compare the mass of the initial mother, sometimes it's called the mother nucleus, to the daughter nucleus and the decay particles, right? So we look on that appendix again, we see that the sodium mass, right, sodium 24 mass, we find that on their appendix. We find the magnesium 24 mass, right? A beta particle is massless. The neutrino is massless. And then we see that apparent loss of mass, right? It's smaller. And that apparent loss of mass gets converted into energy. Okay, just like before. Good? Anyone need me to slow down? I feel like I might be going a little bit fast. Okay, silence means we're moving on. Here we go. Gamma decay. All right, here's for gamma decay. Gamma decay is a photon, right? So if you notice, you can see here in the depiction, gamma decay is when that excited electron releases energy as it falls back to its ground state, right? We did that in our last unit, or in the last chapter in the book. We dealt with in the quiz we just took, but now we're giving it a name, and we're looking at the energy, specifically the energy released. All right, so here's an example, starting with boron 12. It could have beta decay and become carbon 12 and release in the process 13.4 mega electron volts gets released, or for whatever reason, in the process of the beta decay, it becomes carbon 12, an excited state, and the electron is in an excited state. That releases 9 mega electron volts. And then once that excited electron returns to its ground state, that's called gamma. It gives off the gamma, the gamma photon, and releases more energy. And you notice the total release of energy is the same, which it would have to be, right? Because of the mass difference. Okay. All right, more silence. So we're moving on. All right, just as kind of a summary of what we just did, right? So alpha decay, conservation, right? Conservation of nucleons, right? A to A minus 4 because of the 4 in the alpha particle. Conservation of charge, Z protons, Z minus 2 plus the 2 in the helium. Protons in the helium nucleus, the alpha particle. Beta decay, same thing, whether it's an electron or a positron. This is called electron capture. The third one here in this beta decay is called electron capture. I will admit that is a weakness of my understanding of decay, of nuclear decay. I don't know how. It seems contradictory, because if it's decaying, it should be giving off things. It should be falling apart. And here in electron capture, it's actually growing. It's gaining. The nucleus is gaining something. All right, so you can read about that in the textbook, electron capture in beta decay. I read it again, and I'm still not convinced I understand. And then finally, gamma decay, right? That's just kind of a summary of what we just went through. Okay. We are cruising along here. Last slide for today, and then I'm going to stop talking and let you guys go, right? The rate of decay, and that's what we're going to do that's what tomorrow's lab is going to be, as you can see at the bottom of the slide, right? The rate of decay. How fast does this happen, right? And we're going to work on that and try and figure that out in our lab process tomorrow. But you can see a couple of things about it, right? It's totally random. You have this set of nuclei for whatever the radioactive material is, and then any given random nucleus will decay. And the fact that one decays doesn't have any effect on any of the other decays. So if one decays, it doesn't mean the one right next to it's going to decay next. We don't know what order, which ones will decay first, which ones will decay last. We have no way of knowing that, but we can predict how many will be given it will decay in a given time period, and that's what the activity is tomorrow. The lab activity is, right, figuring out how many will decay per time, not which ones, but how many. Okay. And like I said, that's tomorrow's lab activity. So, anyone have any questions? If that's the case, I'm going to stop sharing and I'm going to stop recording here. Stop the share. And how do I stop? There it is. Stop the recording.